Today, I want to talk about defending uptime with OT-SDN segmentation strategies. Because when we think about uptime, it's easy to focus only on cyber attacks. But the truth is, uptime is also threatened by faults, mistakes, misconfigurations, human errors, and even well-intended maintenance. To truly defend your operations, you need more than just perimeter security. You need a segmentation strategy that protects your infrastructure and your uptime, no matter what the source of disruption. This presentation was originally delivered at the Automate Show's Innovation Stage in Detroit in May 2025, where we explored how OT-SDN brings together network visibility, control, and resilience to support both cybersecurity and continuous operations in industrial environments. Hello everyone, it's great to be here and thank you for coming. My name is Thomas Wahlsen, I'm from Sweden and I'm the product manager for network security solutions at HMS Networks. You might know us better as E1 or Anybus. We recently merged with Red Lion Controls and are now integrating their products in our portfolio, an exciting step for us to strengthen our industrial offering. Let's be honest, security is still too often an afterthought. Networks, especially in industrial environments, have traditionally been designed for speed and availability, not security. In manufacturing, cybersecurity has often lagged in the digitization journey. The World Economic Forum highlighted this in a report already a few years ago, naming manufacturing the most targeted sector for cyberattacks. It's been like this 3 years in a row. Why? Because manufacturing has embraced rapid digitization to improve efficiency, sustainability, and enable Industry 4.0. But this transformation comes with a cost. Manufacturers also tend to have a high willingness to pay when downtime strikes, because the impact is huge. And that, of course, makes them a prime target for attackers. It is important to understand that these threats are real. While most still are IT threats, they are reaching deep into the OT environments and getting focused. This is no longer theoretical. Gartner predicted that this year, cyber attacks will have a direct impact on human safety, if this is not the case already. Most attackers are financially motivated, and now malware is evolving specifically for OT environments because it's more impactful and frankly more effective. The consequence, cybersecurity vulnerabilities in OT are becoming a safety risk. This is why it's no longer optional. Implementing robust cybersecurity frameworks is a necessity. Change is not only driven by threats, however, it is also being pushed by regulations. In Europe, the NIS2 directive went into effect last October. It requires proactive action from executive teams, and manufacturing is now officially designated a critical sector. Together with upcoming Cyber Resilience Act that requires products to be secure by default before they can be sold on the market, they promise a much more secure world. But relying on devices for getting into shape to provide self-protection, is this really the answer for our existing environments? In the US, executive orders are creating similar urgency, especially for asset owners in the industrial sectors. And NERC-CIP has put strict requirements on the US energy market since a few years back already. But is waiting for regulation really the answer? We already have excellent frameworks like ISA/IEC 62443, which help harden infrastructures and guide best practices. But here's the challenge. These frameworks are still optional, and they take time, strategy, and maturity to implement properly. That said, we're increasingly seeing insurance companies stepping in and mandating cybersecurity controls as a condition for coverage. This is another strong incentive for change. Despite all this, too little action is being taken. Why? Because many asset owners are overwhelmed. They don't know where to start or what to prioritize. And this is understandable because everything feels backwards. Security should have been embedded in the network from the start, but it wasn't. And now it's time to reassess the situation, the risks, and put the right protections in place. But before we do that and dive into solutions, let's take a step back. How did we get here? Why is the status of security in manufacturing the way it is today? Let's start with an industrial security reality check. Why is manufacturing so impacted heavily? One major reason is the widespread use of Windows in industrial environments. Coming from a telecom background myself, I can tell you, we had one golden rule: never run Windows in operations. But in manufacturing, Windows is everywhere, powering HMIs, SCADA systems, sometimes even PLCs, and more. Windows is a capable platform, but it's also a general purpose and open platform, which means more risk. The CrowdStrike incident this summer made that painfully clear. And let's be honest, Windows is hard to harden, and keeping it up to date is even harder. Can you really reboot an entire factory every patch Tuesday? All this is resulting in significant vulnerabilities on the factory floor. But it is not just Microsoft's fault. Another major issue is the long lifespan of industrial systems. We still encounter machines running Windows 95 or even DOS, kept alive by hope, with no updates, no spare parts, or no recovery plan. It should really be illegal for somebody to run critical systems on software platforms that are no longer supported by their vendor. There is a fundamental mismatch. OT systems are expected to run for 20 to 30 years. IT systems are considered outdated after maybe 5. This is why we need to build security-aware solutions and not legacy holdovers. And there's another often overlooked issue. Industrial protocols themselves are inherently vulnerable. Protocols like Profinet, Ethernet IP, and Modbus lack basic security features: no authentication, no encryption. Anyone with access to the network can send commands or reconfigure devices, even if the web interfaces are secured. This is a major blind spot. So what do we have? Unhardened environments, no availability for patching or no way to install them, open services and insecure protocols. All of this leads to highly vulnerable systems that are difficult to defend. But there are other reasons as well. We're dealing with systems and networks that are often insecure by design. Some compelling research from Orange Cyber Defense highlighted this. They found that the average CVSS score, that is the common vulnerability scoring system for vulnerabilities in the manufacturing sector, is 33% higher than the global average. The CVSS measures how severe a vulnerability is in a piece of equipment. They analyzed vulnerabilities across all sectors, and the takeaway was clear. Equipment used in manufacturing is, on average, significantly less secure. That's bad news. And you might say, well, it's not much of a wonder when the sector runs so much Windows. Fair enough. But it still means that we need to apply a higher level of cybersecurity just to reach baseline protection. Another major factor is underinvestment in security. Historically, manufacturing has allocated a much smaller portion of IT budgets to cybersecurity than other sectors. For example, healthcare typically spends 13 to 14% of IT budgets on security. Manufacturing, around 6%. This gap has to close, and it must happen in the next few years if we're going to keep critical operations safe. Finally, network evolution is also a major driver for change. Traditionally, industrial networks were built as isolated air-gapped networks. They often used technologies like serial buses, which made it hard for outsiders to interfere. Sure, a hacker could target a PLC, but to actually disrupt the physical process, deep system knowledge was needed. Stuxnet is a well-known example, but successful attacks like that have been very rare. However, as we've seen in our annual HMS Industrial Protocols report, networks are rapidly changing. Industrial systems are increasingly built on standard Ethernet, using IP as an underlying transport protocol. To stay air-gapped, many networks have been designed with multiple interfaces on a PLC, forcing network traffic to bridge through it, mimicking the old serial bus model. But remember, a PLC is not a router. This design may limit some threats, but it does not eliminate them. Other Ethernet-enabled devices can still be physically connected to the network, increasing the attack surface. Physical access was once a high barrier, now it's often just a cable away. And more critically, the approach blocks innovation. For true digital transformation, new tools need access to both networks and assets. So networks are changing. The PLC is just becoming one node on a broader, more open architecture. Other systems are granted direct access to the industrial network. And this opens access, enables faster digitalization, but also comes at a cost. A much larger threat surface and increased risk of downtime. Malicious actors now have potential access through the IT infrastructure. In short, underlying network technologies enable innovation, but also increase risk. And this balance must be managed carefully. The result? Incredibly open, flat networks like these. This should be alarming. In networks like these, single threats can come from anywhere. And once inside, they spread like wildfire because there is no segmentation, no containment. We see this far too often, and frankly, it's a huge risk. And let's not forget, external hackers aren't the only risk. Downtime in factories can have many causes. It's not always about cyber attacks. Downtime can result from misbehaving equipment or aging components, poorly configured or overloaded networks, physical issues like damaged or low quality cables, insider threats, both accidental and intentional. The oops factor is a major cause for disruption. And yes, also external cyber attacks. Don't underestimate them, but don't forget the others. We need protection, visibility and control all working together. Ideally, this capability should have been embedded in the network from day one, but it's not too late. The right architecture can still fix it. So let's discuss solutions. The promise of segmentation. As a wise hacker said, if I can't reach it, I can't attack it. Segmentation creates boundaries. It limits the blast radius. By isolating systems, we reduce the attack surface and contain potential threats. This is a simple principle, but a powerful defense. The core of any protection strategy is segmentation. Segmentation between networks, between machines, and ultimately between individual assets. Of course, you already have an enterprise firewall between the internet and your office IT network. Its job is to stop unwanted traffic from coming in, but also allow outbound traffic so employees can use the web and cloud services. Next, you should separate OT from IT. And following a defense in depth best practice, this firewall should be from a different vendor, because the job here is completely different. In OT, you need to be restrictive in both directions. Threats can come from anywhere: visiting contractors, remote access, neighboring machines, insiders, or even from IT. This is exactly why asset owners are advised to isolate their critical machines. Build walls around them, make them self-sufficient, and form smaller, manageable islands inside your network. As small as possible, while it's still practical to operate. This is a strategy that it delivers protection, visibility, and control over your traffic and your production processes. The IEC 6244333 standard is an excellent source for guidance. It defines the security requirements at a system level, requirements that can be applied to machines, lines, or entire plants. It starts with an impact analysis for each system or machine. You evaluate what the consequences would be if that system were compromised, and whether in terms of safety, production, or business continuity. Based on the analysis, you define target security levels for different zones in your network. But then separate these zones using conduits, controlling paths that enforce your security policies. Typically, a conduit is implemented with an industrial firewall. This is a great strategy, but in practice, many teams struggle with what it actually means and how to apply it effectively in their own environments. But what does it actually require? Let's break it down, starting with SR 5.1 network segmentation. This means separating control systems from non-control systems, isolating safety critical systems, and separating machines based upon their required security levels. The physical segmentation between these zones must be a conduit, typically a firewall or a security gateway, depending on the use case. Followed by a core principle, denied by default. Only allow specific, necessary traffic that is explicitly required for the processes to function. These controls are mandatory for security level 2, which in general seems as a minimum bar for securing industrial systems designed under 62443. So in summary, segmentation according to 62443.33 at SL2 requires firewalls or equivalent conduits between zones with strict monitoring and control of interzone traffic. So how do we actually implement segmentation? There are several technology options, each with different trade-offs. One approach is to air gap, use diodes, or use protocol gateways or couplers. These allow only specific industrial traffic through, blocking everything else. And while this can really enhance your isolation, it also limits visibility and flexibility, making it suitable only for very specific use cases. A more traditional approach is using VLANs for logical segmentation. This is common, requires managed switches. However, VLANs lack policy enforcement and can be difficult to manage at scale. They require an enforcement point, like a layer 3 router. A more robust option for security level 2 is using firewalls as conduits. This provides physical separation and enables deny by default policies to strictly control interzone communication. And finally, the most modern method, OT-SDN, software-defined networking. This enables central orchestration of segmentation, making the network programmable. You can define traffic security policies per device, achieving through micro-segmentation and embedding security directly into the network infrastructure, as it should have been from the start. Now let's walk through the pros and cons of each of these models. Let's start with how logical segmentation works. It's typically implemented using VLANs from managed switches. A managed switch assigns specific ports to specific VLANs. This enforces logical separation between devices, even if they share the same physical switch. Access control policies on the switch determine who can assign ports to VLANs, and each VLAN usually represents a zone in your architecture. Any traffic that needs to move between zones, or VLANs, must go through a routing point. At this point, you can apply security policies to restrict or allow traffic. This is often done using a firewall that enforces traffic rules between zones. This setup provides the foundation for 6244333 Security Level 1, meeting the requirements for basic logical segmentation in your network. To meet Security Level 2 requirements, we move from logical to physical segmentation. This means that using separate switches for each zone and using either dedicated firewalls or firewalls with separate physical network interfaces. In this setup, any switch will do because it's isolated to its own zone. There is no need for VLANs since this physical separation enforces the boundary. Of course, using high-quality managed switches is still a good idea, but even unmanaged switches work well here from a security standpoint. Any traffic that needs to move between zones must go through the firewall. There, it's routed between physical interfaces and rules determine what traffic is allowed to pass. This setup achieves logical segmentation aligned with 62443 SL2 and higher, using separate layer 2 infrastructure connected to different firewall ports. Why traditional segmentation falls short? Traditional segmentation focuses heavily on the north-south traffic flowing between the IT and the OT layers, but largely ignores the east-west traffic within the OT network itself, where lateral movement often happens during an attack. And let's be honest, the Purdue model is widely referenced, but it's not a security model. It's a reference architecture. It was not built with modern cyber threats in mind. So the result, multiple layers of static, inflexible rules, large zones that often allow much internal movement, and a network that is complex to manage and slow to adapt. To defend against today's threats, we need dynamic segmentation that protects both between and within the zones. Introducing OT-SDN, Software-Defined Networking for Zero Trust Access. OT-SDN brings zero trust principles into industrial networks, enabling security that's both granular and automated. Key capabilities of software-defined networking for OT include centrally orchestrated programmable network, policy-driven centralized control, a deny by default rule set. For new devices, they will automatically be blocked from all ports unless explicitly allowed, and very tight traffic control. Only approved protocols between specific devices, no unsolicited traffic. And it's purely designed for industrial needs. Automatic rerouting if a path between endpoints fails, and security posture rebalancing. If a device is moved, security policies just adjust and move with it and adjust automatically. Here is how it works. Software-defined networking for OT provides a central orchestrated programmable network. What makes it so OT specific is that it also uses device identification, not just traffic control. It all starts with an open flow capable switch. These work much like managed switches, but they support the open flow open source protocol. These switches connect to a central orchestration controller. This network access request All network access requests will go through this controller. Devices will identify themselves typically by MAC address, but the controller can go further. For example, it can open an Ethernet IP SIP path and start polling the device, requesting additional information like the device serial number. And once the device is identified, the controller assigns traffic policies to that specific device. The policies are then pushed over to the switches, and from that point on, the switches enforce the policies locally. Traffic does not depend on the controller once it's flowing. You can define exactly what is allowed. For example, traffic from a specific PLC to a specific robot using only approved protocols. If someone plugs in a new device, let's say a visiting laptop, it's immediately denied access, even if it's on the same port a PLC was using earlier. This truly gives you simplified networking, maximum control, and microsegmentation at the device level, dynamic security policies, and full real-time visibility. OT-SDN brings zero trust networking into the industrial space with centrally managed, deny by default SL2 level policies for every device. Here is what it can look like in the orchestration software. A fully automated real-time network map. In this view, you can see the PLC connected to a switch on the left. It's attempting to communicate with a device named Fusion on the right. The connection between these two devices is governed by strict traffic policies. Only ICMP, SIP, HTTPS, RDP, and IPAir3 are allowed. All other protocols are automatically blocked. Meanwhile, the switches are constantly sending over flow reports to the controller. This enables near real-time visibility of observed traffic, breaking it down by protocol, giving operators both insights and control. In addition to simplified management, OT-SDN architectures also bring powerful benefits around resilience. In an OT-SDN network, resilience is built in. It's a self-healing network. Here's a visual example. A centralized SDN controller manages 4 switches connected in a ring or even cross-connected for redundancy. Traffic between 2 devices takes the shortest path. In this case, traffic from the HMI on the bottom left to the HMI on the top right travels through 3 switches using the northern path. Now, if a link fails somewhere in the network, the SDN controller detects it immediately and reroutes the traffic automatically, using an alternative path through the switches. The failover happens in milliseconds. No need for spanning 3 protocols, no need for proprietary failover mechanisms. This resilience is native to the SDN design. Here we have a table outlining 3 segmentation strategies shown side by side. Logical segmentation with VLANs, physical segmentation with firewalls, and orchestrated segmentation with OT-SDN networking. Let's compare these 3 approaches across a few key challenges that often come up with segmentation. We'll start with manageability, next insights into the traffic, operational resilience is another big factor, and then there's security, and finally the ease of installation in the brownfield environment. Let's start by comparing the 3 approaches from a manageability perspective. Logical segmentation with VLANs. In this approach, it requires manual configuration of switches and firewall rules. It's typically a distributed setup, and while some vendors offer proprietary tools for centralized management, these tools are often limited in capability. They also tend to increase vendor lock-in, which can become a long-term burden rather than a benefit. Physical segmentation with firewalls. In this scenario, it can require physical changes to the network architecture, such as a separate switches and cabling per zone, and firewall rules will need to be managed, usually on distributed individual units, which adds to the administrative overhead. Vendor solutions may help providing centralized approaches, but it always remains a challenge to get a grip of the hundreds of thousands of rules needed over a distributed architecture. Orchestrated segmentation with OT-SDN, however, here you gain centralized control through the controller. It simplifies the security management of all assets, reducing configuration errors and making policy changes easier to deploy and maintain across the entire network. Now let's look at each approach from an insights into the traffic perspective. VLANs themselves do not inspect or analyze traffic. You may get basic port counters for traffic volumes or errors, but that's it. Some switches provide mirror ports that can be used to feed third-party monitoring tools. This typically requires local probes on each switch, and it increases the complexity and the cost significantly. With physical segmentation, with firewalls, they offer some visibility into the traffic flows, especially on the north-south traffic, the traffic that is crossing between the zone boundaries. Logs can be exported via syslog, and mirror ports at a key aggregation points can provide traffic insights very deeply. But east-west traffic within zones remains harder to see unless more probes and segmentation is added. And finally, orchestrated segmentation with OT-SDN delivers deep, dynamic, and centralized visibility. It provides real-time insights into traffic between any two devices, including both north-south and east-west flows. Every communication path is visible, showing exactly who's talking to who, using what protocol and when. And with real-time mirroring, you can tap any flow for analysis. No need for local probes. Next, let's evaluate operational resilience. VLAN-based networks rely on traditional failover mechanisms like spanning tree protocol. This introduces convergence delays and potential loops. Worse, VLAN misconfigurations can easily cause widespread outages, making troubleshooting time-consuming and risky. Firewalls, on the other hand, can improve isolation, but to achieve resilience, you'll need dual hardware setups with synchronized configurations. This adds to the cost and complexity, and failover depends on proprietary or manual recovery mechanisms, and resilience is only as strong as the configuration discipline. OT-SDN delivers resilience by design. Its dynamic path and automated failover, the network self-heals in the event of a link or device failure, without the need for spanning tree, redundant firewalls, or external protocols. Failover occurs in milliseconds, keeping operations running smoothly even during disruptions. Now let's compare the security capabilities of each segmentation strategy. VLAN operate at layer 2, meaning policies are hard-coded based on MAC addresses and port assignments. There is no layer 3 control, no protocol filtering, and no way to inspect or restrict specific traffic types. Security here is minimal and configuration errors are hard to detect. Firewalls provide layer 3 protection control, and you can create rules based on IP addresses, TCP UDP ports, and network zones. Advanced industrial firewalls may also offer deep packet inspection, DPI, for layer 7, enabling more granular control over specific industrial protocols like Modbus or SIP. This improves security significantly, but requires manual configuration and upkeep. OT-SDN brings security to a whole new level. It combines the layer 2 endpoint identification using MAC addresses with industrial protocol polling like Ethernet IP or SIP. to verify the identity and function of each device. Then it allows policy enforcement at both layer 2 and layer 3 level. You can allow only EtherCAT or Profinet I/O between two devices and those protocols that run directly over Ethernet. Or you can restrict communication by TCP/IP UDP ports, allowing only specific IP-based protocols like Modbus or OPC UA. This gives you full flexibility with precise control over both north-south and east-west traffic. It's granular, adaptive, and perfectly aligned with zero trust principles. Finally, let's consider the implementation effort in existing brownfield environments. Implementing VLANs typically requires replacing unmanaged switches with managed ones, and then manually configuring VLANs and access rules on every switch. To secure the network, you also need to add firewalls, increasing setup time and complexity. With physical segmentation using firewalls, you can usually keep your existing switches, and you can use a bridge mode to transparently add security and separate traffic between zones. Implementing this can be disruptive and time-consuming, especially in live environments. OT-SDN offers the least disruptive path for brownfield operations. You can replace switches within your existing architecture, whether they are managed or unmanaged, and simply connect them to a central orchestrator. From there, you can run it in learning mode, automatically absorbing the traffic patterns to help define your policies. It's by far the easiest approach when it comes to engineering and maintaining security policies. So while these three strategies have their place, OT-SDN stands out by combining visibility, resilience, and security, and manageability, all without disrupting your existing setup and architecture. So in conclusion, security and uptime go hand in hand. You can't have reliable operations without securing the systems that support them. It's time to move from reactive to proactive security. Waiting for incidents is no longer an option. Segmentation must be built into your networks and your network architecture from the start. So the key takeaway is this: choose technologies that make it easier to defend your uptime. Because in today's connected industrial environments, resilient networks are secure networks. Thank you very much for today. Feel free to reach out to us for more information.